0-day brief.
Um, you know that really annoying captive portal you hit on airport Wi-Fi?
Oh, yeah, the one where it's like you have to type in your room number or last name before you can finally check your email.
Exactly, yeah. It just feels like, I don't know, the most trivial piece of software imaginable.
Right, totally harmless.
But today, that exact same harmless login page is literally the reason unknown threat actors hold root access to tens of thousands of top-tier enterprise firewalls.
Which is just wild to think about. We're looking at a stack of threat intel briefings and vulnerability reports from this month, so May 2026.
Yeah, and they detail an absolute security crisis for Palo Alto Networks because that little captive portal, the User-ID Authentication Portal, officially it ships natively on every single Palo Alto PA series hardware and VM series virtual firewall.
Meaning we are talking of an attack surface of roughly 85,000 enterprise customers, like Fortune 500 companies, federal government agencies, massive defense contractors.
All of them.
Yeah, they are all running the specific login page canon on devices that sit, directly on their network perimeter, just facing the open internet.
So our mission for this deep dive is to sort of unpack the mechanics of how this ubiquitous speed bump on the internet became the downfall of the most trusted security appliances in the world.
And, maybe more importantly, dissect the massive blind spot in how the tech industry actually engineers and procures enterprise security.
Right. Okay, let's unpack this. We have to start with the vulnerability that kind of set the whole house on fire.
Yeah, that would be CVE 2026-0300, which was published on May 6th. The core issue here is a CWE 7887.
Which is an out-of-bounds right vulnerability.
Exactly. And it's located in the pre-authentication code path of that captive portal daemon.
Pre-authentication being the really critical factor here.
Oh, absolutely. Because before the system even attempts to validate your credentials, like before it knows if you're a legitimate user at all, it has to parse the raw network requests you send just to load the login page.
Right, the daemon is handling those incoming HTTP GET requests and pulling that data into fixed-length memory buffers.
Yeah, and because this daemon is written in C, it relies entirely on the developers to, manually enforce the boundaries of those memory buffers.
So it's kind of like the firewall has this fixed size bucket for incoming data, right?
That's a great way to look at it, yeah.
But the code doesn't actually check if your data is going to fit before it just starts pouring it in. So when an attacker sends this massive, carefully crafted payload instead of a standard web request, the bucket just overflows.
Right, the C code fails to validate the size, and it just keeps right and past the end of the allocated buffer, which ends up overwriting the adjacent memory space on the firewall.
And this is where it goes from like a simple software crash to a total catastrophe.
Because that adjacent memory space isn't just empty storage, it actually contains the execution stack for the daemon itself.
Oh, wow.
Yeah, so by overwriting the instruction pointer, which is basically the part of the memory that tells the processor what to do next, the attacker can force the firewall to execute their own malicious shellcode.
Shellcode that was just hidden inside that oversized packet.
Exactly. And because this specific captive portal process runs with really high system privileges within the firewall's OS, the attacker isn't just hijacking a web server.
They inherit those high privileges.
Right. It results in an instant root shell.
Which means 0 clicks required. Like you don't need a password, you don't need some insider threat, or an employee falling for a phishing email.
Nothing like that. You just send a single weaponized network packet to the front door, and the firewall hands you the keys to the kingdom.
Which totally explains why I got a CVSS severity score of 9.3 out of 10.
Yeah, a 9.3 is massive. And it's important to note, this wasn't just theoretical research.
Right. Palo Alto's own threat intel division, Unit 42, actually confirmed this was being actively exploited in the wild.
Yes, before the CVE was even assigned, unknown attackers were already automating the exploit.
Just scanning the whole internet.
Exactly, scanning global IPv4 ranges for exposed captive portals and silently collecting root shells everywhere.
So why does root on a firewall matter so much? I mean, obviously root is bad, but a firewall is just routing traffic, right?
Well, the implications are profound because of the specific hardware. If a threat actor gets root on, say, a random application server in your DMZ, they own that server and maybe the databases it talks to.
Sure.
But if they get root access on an enterprise firewall, they own the entire topology. The firewall is the absolute choke point for the corporate network.
Right, because it terminates the VPNs and enforces the segmentation between your highly secure enclaves and your standard network.
Exactly. And it also brings us to the TLS decryption pipeline.
Oh, right, the SSL forward proxy stuff.
Yeah, most large enterprises aren't just using firewalls to block ports anymore. The firewall actively intercepts outbound secure web traffic.
It presents a dynamically generated certificate to the employee's machine, right?
Yes, and then it decrypts the traffic to inspect it for malware or, data exfiltration before re-encrypting it and sending it out to the web.
So if an attacker has root privileges on the device doing that decryption,
They can just bypass the inspection engine entirely. They hook directly into the memory buffers handling the TLS stripping.
oh man, so they can read everything.
Everything. Plain text, corporate emails, proprietary API tokens, banking sessions, and they can read it directly from RAM before the data is ever re-encrypted.
It's literally the ultimate observation post, just sitting there watching every piece of sensitive data flow past in clear text.
It really is. It's the absolute worst case scenario for an enterprise.
But wait, this highlights a massive contradiction to me. We are talking about an unauthenticated buffer overflow in C code, right?
Right.
Isn't a buffer overflow a classic, like, 1990s style bug? I mean, this is the exact bug class that gave us the Morris worm in the 80s and Code Red in the early 2000s.
Yeah, it's an incredibly old class of vulnerability.
So how does a 25-year-old bug class end up sitting on the perimeter of a 2026 leading next-gen firewall?
Well, answering that requires looking at the architecture of the appliance itself, which was actually laid bare exactly 1 week after that first vulnerability dropped.
Right, because if one 90s-style bug is a fluke, 8 is a systemic failure.
Exactly. On May 13th, Palo Alto released an emergency barrage of 7 additional CVEs.
The scale of that May 13th cluster is just staggering. I mean, we saw a buffer overflow in the IKEv2 handler, right?
Yeah, IKEv2, which is the protocol that manages the really complex cryptographic negotiations for VPN tunnels.
And because it requires heavy packet parsing before a connection is even established, it's a massive attack surface.
Huge. You send a malformed ISAMP packet during the handshake, overflow the buffer, and you own the box.
Then there was a heap overflow in the DNS proxy service, too.
Right, the service that intercepts DNS requests to block malicious domains. Send a slightly oversized DNS response, and you achieve remote code execution.
And the cluster had some severe logical flaws, too, not just memory corruption, like CVE-2026-0257.
The GlobalProtect Remote Access VPN one, yeah, that was an authentication bypass via cookie manipulation.
Millions of employees rely on GlobalProtect daily.
And the vulnerable daemon improperly validated the cryptographic signature of the session cookie. So an attacker could literally forge a cookie structure.
Just tricking the system into believing they had already passed primary authentication and MFA.
Exactly, dropping them straight into a valid, authorized VPN session.
We also saw a cryptographic signature bypass in the cloud authentication service, right?
Yeah, where the firewall failed to properly verify identity tokens from providers like Azure AD or Okta.
Plus a command injection bug in the administrator web interface, and another certificate bypass in the GlobalProtect app itself.
It was 8 critical or high-severity CVEs in a single month.
But looking through these threat intel reports, the most shocking data point is where these vulnerabilities were not located.
Right, 0 of these bugs were found in the core firewall rule engine.
Exactly. The core data plane was totally fine.
Yeah, that highly optimized code that processes security rules, applies app ID signatures, and decides at line rate whether to block or allow a packet, it was entirely pristine.
Every single vulnerability in this massive cluster resided in what we call an auxiliary service.
Right. What's fascinating here is how attackers are looking at the architecture.
It's like the castle analogy. You buy a top-tier castle, the firewall, to defend your enterprise network kingdom.
I like this analogy. Let's hear it.
So the core rule engine is the heavy iron drawbridge and the massive stone walls. You pay a premium for it, and it's rock solid. 0 CVEs.
Impenetrable.
Right. Attackers know they can't just mount a frontal cavalry charge against that drawbridge, but the castle needs auxiliary entrances to actually function.
Right, you need a way to get supplies in.
Exactly. The captive portal is like the 30-year-old wooden kitchen door used for deliveries. The DNS proxy is the sewer grate draining into the moat.
GlobalProtect is the servant's passage out back.
Yeah, and IKEv2 is a pigeon coop on the roof with a ladder leading directly down into the throne room.
That's spot on. And attackers are automating this. They build massive scanning arrays using tools like Shodan and Senses, not to test the strength of the drawbridge, but to map the perimeter.
They're just walking around jiggling the handle on every single wooden kitchen door,
Yeah.
and sewer grate.
Exactly. They hunt exclusively for these auxiliary daemons because they know those services parse untrusted, highly complex internet traffic.
Which forces us to ask why those side doors are so incredibly fragile in the first place. I mean, hold on. I struggled to let the vendor off the hook here.
I get that.
Palo Alto operates Unit 42. They employ some of the best vulnerability researchers on the planet, constantly finding 0 days in other people's software.
They do, yeah.
So how do they miss an unauthenticated buffer overflow in their own captive portal daemon? Isn't this just vendor negligence?
Well, it's not just about negligence. I mean, Palo Alto is patching and disclosing responsibly here. It actually comes down to a structural pattern embedded deeply in the entire industry.
The appliance model.
Yes, exactly. When an enterprise procures a high-end firewall, especially from a vendor that's dominated the Gartner Magic Quadrant for over a decade, they fall into this psychological trap.
They treat the box as a monolithic, magical shield of pure security.
Right. But underneath the sleek marketing and the metal chassis, it's essentially just a customized Linux or BSD kernel.
Orchestrating a massive array of separate user space daemons written in C and C++ faux.
And those daemons are totally disparate code bases. The core data plane might use custom ASICs or a rigorously audited memory safe code.
Because that's the flagship differentiator, right? That's what they sell.
Exactly. But the management plane and the auxiliary services, they're often legacy code.
Built by different engineering teams over many years.
Or even acquired from third-party companies 15 years ago and just bolted onto the main OS to satisfy a procurement checklist.
So they're parsing untrusted input without the same intense security auditing that the core engine receives.
Right. The vendor incentives are entirely skewed toward the core engine. That's what gets the relentless penetration testing and architectural threat modeling.
While the auxiliary services like a captive portal for guest Wi-Fi sit in a blind spot that nobody really owns.
The customer assumes the vendor secured the entire box, and the vendor focuses their resources on the features that drive market share.
You know, this maps perfectly to the architectural flaws we uncovered in our previous deep dive on the GOGS Git server.
Oh, the whack-a-mole architecture episode, yeah.
Exactly. In that scenario, the maintainer spent 2 years patching 4 separate argument injection bugs, just playing whack-a-mole with individual CVEs.
But they never stepped back to audit the fundamentally flawed way the application passed data to the Git binary.
Right. They ignored the fifth door, which was sitting wide open the whole time.
The parallel is exact. It's just scaled up to the highest levels of enterprise network security here.
The vendor patches the drawbridge flawlessly, but fails to conduct a holistic architectural audit of the pigeon coops and the kitchen doors.
And now we're seeing 4 different memory corruption flaws across 5 different auxiliary daemons on the exact same operating system.
It really reveals a reactive security posture driven by the illusion of the monolithic appliance. Features are just bolted on and ignored until a sophisticated threat actor forces a crisis.
And since threat actors are actively automating these exploits to find open side doors right now, waiting for a standard patch cycle is just not an option.
No, definitely not. We need to look at what operational levers enterprise network teams and federal supply chains can pull immediately.
The urgency really cannot be overstated here. As of May 29th, so yesterday, relative to us right now, CISA officially added the GlobalProtect authentication bypass to the KEV catalog.
The known exploited vulnerabilities catalog,
Wait.
which triggers binding deadlines.
Yes. Federal agencies and any organization in the federal supply chain are legally mandated to remediate the vulnerability within a highly compressed timeframe.
So what are the specific fixes required?
For organizations running the hardware and VM series firewalls on PAN-OS, you have to apply the specific version patches released by the vendor.
Which versions are we talking about?
Administrators must upgrade to versions 12.1.7, 11.2.12, or the 11.1.0 hotfix 25 branch and above.
Okay, to seal the memory corruption flaws across the daemons.
Right, though it is worth noting that cloud-native deployments like Cloud NGFW and most of Prisma Access, they operate on a different architecture.
So they're largely insulated from this specific cluster.
Yes, mostly. But for everyone else, enterprise patching at the perimeter is notoriously difficult.
Oh yeah, change management boards, testing requirements, the sheer operational risk of rebooting a core firewall, it always delays deployments.
Which is why if an infrastructure team absolutely cannot push a PAN-OS upgrade tonight, they need a robust workaround for the 0 day that's actively bleeding data.
So what's the workaround for the captive portal, the CVE 2026-0300?
It requires an immediate configuration change to the control plane. You have to restrict the User-ID Authentication Portal so it only binds to trusted internal IP spaces.
Basically, never let it face the internet.
Exactly. If the portal is strictly required for guest Wi-Fi onboarding, it must be isolated entirely to the specific guest VLAN.
Right, the daemon handling those pre-authentication requests cannot, under any circumstances, be exposed to untrusted external zones.
But even with mitigations in place, the challenge really shifts to incident response.
Because these are technique-level vulnerabilities.
Right.
Right, they target the memory architecture, so the standard forensic playbook doesn't really apply.
Precisely. An attacker exploiting a buffer overflow in the IKev2 daemon doesn't drop a malicious executable to the hard drive.
So there's no traditional malware file hash for an endpoint detection system to flag.
No. The entire exploit lives dynamically in the memory space of the compromise process, which mandates a shift to behavioral detection methodologies.
And so SOC analysts need to look for external IPs hitting the portal, right?
Yes, and they need to hunt for anomalies in the management plane telemetry.
Like unexpected root shells spawning.
Exactly. If the captive portal daemon suddenly spawns a bash shell or an interactive SSH session as a child process, that is an immediate indicator of a root compromise.
That makes total sense. What about the VPN bypass?
For that, analysts must scrutinize VPN logs. They're looking for successful tunnel establishments that completely circumvented the standard authentication workflows.
Like missing multi-factor authentication handshakes or weird session cookie structures.
Right. If we connect this to the bigger picture, though, you cannot protect a door if you don't even know it was built into the wall.
Which means the real remediation extends way beyond just a software update. It requires an operational mandate.
Yes. Infrastructure teams need to force their vendors to provide comprehensive architecture diagrams mapping every single listening daemon on the box.
Because if a network engineer doesn't know exactly which legacy web servers are bound to the public interfaces of their firewall, that's a catastrophic blind spot waiting to be exploited.
We've spent decades assuming the security product is doing the auditing for us. We forget that underneath the bezel, it's just software.
Inherently vulnerable to the exact same memory corruption flaws we've been battling in C code for 30 years.
The appliance model abstracts away the complexity, but it does not remove the risk.
No, it doesn't. We started this journey looking at the most mundane, trivial piece of internet infrastructure imaginable, right? A harmless airport Wi-Fi login page.
And we watched the C code powering that portal become a zero-click backdoor.
Granting threat actors root access and full TLS decryption capabilities across 85,000 enterprise environments.
It's wild. We dismantled the psychological trap of the monolithic appliance, revealing how the industry hyper-focuses on the core data plane,
while completely ignoring the fragile legacy daemons bolted onto the perimeter. You'd think the firewall's main job is to block attacks, but you'd be wrong about where the attacks actually land.
because they silently compromise the auxiliary web servers running adjacent to the rules engine.
So what does this all mean? Today, the crisis was isolated to the enterprise firewall, but the structural flaw we unpacked applies to the entire ecosystem.
It really does. Think about your own network architecture. Look at your perimeter.
What other trusted black box appliances are currently anchored to your infrastructure?
Load balancers, VPN concentrators, massive enterprise storage arrays.
Right. How many of those expensive, mission-critical devices are secretly running ancient, unaudited web daemons deep inside their management planes?
Just waiting for an attacker to walk up and jiggle the handle on the kitchen door.
Exactly. Keep questioning the tools you trust the most, and remember, a castle is only as secure as its weakest entrance. Thanks for joining us on this deep dive. We'll see you next time.
Thank you for listening to Zero Day Brief.